हेलो डियर फ्रेंड्स। आज की इस क्लास में हम बात करेंगे जो जियो फिजिक्स में हम मेथड यूज में लेते हैं, जो बेसिकली आपके प्रीलिम्स में सिलेबस में भी गिवन है। जियो फिजिकल प्रोस्पेक्टिंग नाम से टॉपिक गिवन है आपके प्रीलिम्स में, टॉपिक नंबर 4 है। उसका एक पार्ट है एलिमेंट्स ऑफ जियो फिजिकल मेथड, in which you have to talk about principles, what are the data reduction techniques, and what are the applications of gravity method, magnetic method, electrical method, electromagnetic method, and the well logging. So in this class, we will mostly talk about the electromagnetic method. We will talk about what the basic principle of electromagnetic method and what are the basic methods we are going to use in the electromagnetic prospecting. Okay, so let's start the discussion. We will cover this topic from the William Lowry Fundamental of Geophysics. Okay, so let's see. This is given topic. So the electromagnetic surveying is the topic given here. We will try to cover mostly this topic from this book. Okay, so let's start the discussion. Here it is written that the Coulomb's law shows that the electric charge is surrounded by an electric field. You know that if you have an electric charge, let's say you have a positive charge, in another case you have some negative charge, then these charges, electric charges, are surrounding by a field which is known as an electric field. Okay, and there will be the direction of electric field. For the positive charge, it is radially outward direction, right? And for the negative charge, the direction of the field, right, you can say that it is radially inward, right? So for the positive charge, electric field direction are radially outward, so it behave as a source of an electric field. And for the negative charge, the field line are inside, or you can say toward the center. Okay, radially inward, so this will behave as a sink of an electric field. So what the Coulomb's law says is that an electric charge is surrounded by an electric field. This electric field exert a force on the another charge. Let's say if you have some if you have a system in which there are two charges, Q1 charge and Q2 charge, then the charge Q1 will have its electric field. When Q2 charge is coming toward Q1, then due to this electric field, this charge Q2 will experience a force. This force is called the electric force. So basically what happens, then an electric field will exert a force on the another charge, causes them to move. Whether it can move toward the charge Q1 or it can move away from the charge Q1, it will depend on the what is the charge nature, whether it is positive charge or the negative charge. We know that the same charge will repel each other, repulsive force will act, and for the same charge the force will be repulsive, and for the opposite charge force will be, you can say, attractive. Force, you can say, it will be attractive. Okay, so this must be clear to you. What the Coulomb's law says is, this is the first thing. Then let's say what the Ampere's law say. Ampere's law show that the electric charge, the moving electric charge, will produce a current, and the direction of current will be opposite to the direction of the flow of electrons. So Ampere's law shows that the electric charge, or you can say current, moving in a conductor will produce a magnetic field which will be proportional to the speed of the charges, right? तो ये आपको ध्यान रखना है. उसके बाद में देखिएगा क्या लिखा हुआ है इसमें. If the electric field increases so that the charge is accelerated, if the electric field is increasing, the charge will be accelerated, and you know that the changing electric field will produce a magnetic field. So this is the one thing which is very very important. Changing velocity or changing electric field will produce an changing magnetic field, which in turn produce the electric field. So this is the basic phenomena of the electromagnetic force. You can see it there on also. There is an electric field is given there. The electric field can be produced by the changing magnetic field, and the magnetic field can be produced by the changing electric field, or you can say by the current. Okay, so these two things are given there, and this is the diagram given for the electromagnetic wave. So in the z direction, the wave is propagating, so direction of the propagation is in the z direction. In the y direction, the magnetic field component is there. In the x direction, electric field component is there, right? And this is defined as the wavelength, right? You can see from there on. Okay, so changing magnetic field will induce a इलेक्ट्रिक फील्ड इन द कंडक्टर्स, दिस इज नोन एज द फेराडेज लॉ। ताकि एग्जाम में बेसिकली इलेक्ट्रोमैग्नेटिक आपका जो प्रीलिम्स का एग्जाम होगा उसके अंदर इलेक्ट्रोमैग्नेटिक सर्वे से एटलीस्ट 2 क्वेश्चन आपसे पूछे जाएंगे। तो आपसे क्वेश्चन पूछा जा सकता है कि फेराडे लॉ ऑफ इंडक्शन क्या शो करता है, राइट। सो यू विल से दैट द चेंजिंग मैग्नेटिक फील्ड विल प्रोड्यूस एन इलेक्ट्रिक फील्ड, राइट। सो बेसिकली होता क्या है, changing magnetic field, changing electric field will produce the changing magnetic field, and then changing magnetic field will produce the changing electric field, and this changing electric and magnetic field will travel with the speed of light, and this wave is known as the electromagnetic wave. So it is written there, the coupling of the electric and magnetic fields is known as the electromagnetism. Okay, this must be clear to you. If two straight conductors are laid end to end and connected in the series, they will act as an electric dipole. So you must know what is the electric dipole means. Basically, an alternating electric field applied to the conductor causes the dipole to oscillate. If there is a dipole and you are applying some alternative electric field, in that case, the dipole will oscillate, and this oscillating dipole will act as an antenna. Very, very important thing. We will talk about that for the emission. And what the antenna does, it will emit the electromagnetic wave. So basically in the electromagnetic surveying we have to use the electromagnetic wave, and this electromagnetic wave will be generated by the oscillating dipole, and this oscillating dipole will act as an antenna. Okay, so this must be clear to you. This electromagnetic wave will consist of one the magnetic field B and another one is the electric field E, which will vary with the frequency of the oscillator. This is very, very important concept. You must remember that an electric field and magnetic field are orientated at a right angle. That means they are orientated perpendicular to each other. It's very, very important concept, and it is perpendicular to the plane of the propagation. So basically electric and magnetic field are perpendicular to each other, and these two are also perpendicular to the direction of the propagation. So this is also very, very important concept that you must remember. Another concept that is important for the electromagnetic wave is that it travels with the speed of light in the vacuum, and the speed of light is given there by the c, 3 into 10 to the power 8 meter per second is the speed, and this is one of the fundamental constant of the nature, right. So basically, you know, the electromagnetic equations, the four Maxwell equations, you know, the four Maxwell equations. First of all, first thing that you must remember is what the Maxwell equation tells about. So Maxwell equation gives the relation between the electric and the magnetic field components. The second thing you must remember is that there are four Maxwell equations. First Maxwell equation talk about the Gauss law in electrostatics. Second Maxwell equation talk about the Gauss law in magnetostatics, which means the divergence of magnetic field is zero. That means magnetic monopole does not exist. The third Maxwell equation talk about the Faraday's law of electromagnetic induction, that tells us that the changing magnetic field will produce the electric field. So you can say that del cross E is equals to minus del B by del T. And the fourth Maxwell equation is the modification of the Ampere's law, which tells about that the curl of the magnetic field. Okay, so that means del cross B will be equals to two terms. The first term is the conduction current term, and the second term is the displacement term, right. So these must be clear to you. The another thing which is important for you, that the Maxwell equations are the coupled equation in the electric and magnetic field. So basically in the Maxwell equation, electric field and magnetic field are coupled to each other, they are not separately in there. Okay, so what we have to do, basically using these four Maxwell equations, we will derive two Maxwell equations which are decoupled. Basically this is very, very important concept. They are decoupled in the sense that the first equation is only dependent on the magnetic field and the second equation is only dependent on the electric field. So these two equations we will use in the electromagnetic surveying. So these two equations must be remembered to you, the first thing. And the second thing which is important there, you can see that in the left hand side of the equation is the spatial variation of the B. Spatial variation, that means del square is the Laplacian operator, and this is given by del square by del x square plus del square by del y square and plus del square by del z square. That means these are dependent on the x, y, z, and which are the spatial component. So you can say that this equation in the left hand side is only the spatial variation, and in the right hand side there are the variation with respect to the time. So there is a term del by del t and another term del square by del t square, and there are two terms. This is very, very important. We will describe what these two terms means. Basically the first term describe about the conduction term. So the first term is known as the conduction term, and the second term is described by the wave equation term. wave equation term. Why? Because if the first term will be neglected, then this equation will become as a wave equation, the as same as the seismic wave moves. And if we neglect the second term, then this equation will be same as the heat equation, right? Or you can say the temperature variation equation, right? Or you can say the diffusive equation. Okay, so this is known as the conduction equation, and similar equation will be for the electric field. So the electric field and magnetic field equations you must remember, the del square in the Cartesian coordinate is defined, is given there, and this is known as the Laplacian operator. I think this is clear to everyone. This diagram is very important for you. There will be the questions in the prelims also. At least one question will be from this diagram. There will be question in the mains also, and for the interview purpose this diagram will be very helpful for you. So let's see what the diagram signifies. Okay, so look at there. Okay, so basically देखिएगा क्या है इसमें. ये जो frequency है, frequency is given in the hertz, and this is the order of increasing frequency. Okay, and this is the order of decreasing wavelength. So this thing must be clear to you. So basically this is the electromagnetic spectrum, which consists of the gamma rays, the X rays, the ultraviolet rays, which we can say UV rays, infrared rays. In between there is a visible light, and then microwave, then radar, then GPR, ground penetrating radar method. One of the very important concept. There will be one question 101% in the prelims exam on the topic ground penetrating radar method. So the first question can be asked that the ground penetrating radar method is used in which of the following method. So there will be four options: gravity method, magnetic method, electrical method, and electromagnetic method. So your answer will be the electromagnetic method. And the second question will be that the ground penetrating radar, at what frequency they act. So you will say that the 100 megahertz to 1 gigahertz this is acting, and this range is in the radar wave, or you can say in the micro, in the radar range. Okay, so this is very important concept. And then there will be the term the electromagnetic induction. Okay, so there is a method known as the electromagnetic induction method. So this method will work on this frequency range 10 to the power 4 to 1 hertz. Okay, and there is the magnetotelluric method is given there, and then binaural and secular variations are given there. Okay, so we will talk about this. So just remember this diagram thoroughly. The visible region range you must clear. That visible region is from 400 nanometer up to 700 nanometer is there. And the gamma rays have the highest frequency. Okay, this thing must be clear to you. So moving into the next thing, let's see what is given there. So in the decoupled equation, there is a term, the sigma, which is known as the electrical conductivity. Another term is mu r, which is the magnetic permeability, which is for the most material, it is close to 1. Mu 0 is the permeability constant or the permeability of the free space. तो mu 0 की वैल्यू आपको ध्यान में रखना है 4 pi into 10 to the power minus 7 Newton per ampere square. Epsilon r is the relative permittivity of the material. Epsilon 0 is the permittivity constant, or you can say permittivity of the free space. And you must remember the value of epsilon 0, permittivity of free space, 8.85 10 to the power minus 12 coulomb square per Newton meter square. And very important concept is given there, that in the constant electric field, this is very important concept that you must remember, that in the constant electric field, the dielectric constant, or you can say the permittivity constant of permittivity of free space, which is defined as the epsilon r, is known as the dielectric constant. So basically relative permeability and dielectric constant are the same thing when we talk about the electric field at the constant. Okay, and this thing is also very important, that the earth, most of the rocks have dielectric constant approximately 5 to 20. For the water it is 80. So this is very important, you must remember. This question can be asked in the examination, that what is the dielectric constant of the water. So you will say that the 80, and this is the unitless quantity. Okay, this is also very important. Then it is written that in sediments and sedimentary rocks, the water content play an important role in determining the value of K. The value of epsilon r increases with the frequency of the electric field. So this concept also remember, that the value of epsilon r, the relative permittivity, will increase the frequency of the electric field. So I think this is clear to everyone. Moving into the next. Electromagnetic radiation encompasses a very wide frequency spectrum, as we have seen above, that electromagnetic radiations up to the gamma ray and from starting from the gamma ray, it goes up to the radar wave and microwaves. Okay, so the gamma ray have the highest frequency, or you can get the shortest wavelength of the gamma ray, and then X-ray, and then up to the lowest frequency of the radio signals. Okay, visible light constitute a very narrow part of the spectrum, and as we have seen that for the visible light, wavelength order is 400 up to 700 nanometer. This is very very important for you. Electromagnetic, two ranges of this is a very very important concept जहां से आपका prelims में question पूछा जाएगा. Two ranges of the electromagnetic radiation are of particular importance in the solid earth geophysics. The first is a high frequency range, a high frequency range in the order of megahertz up to the gigahertz, the very very high frequency range in the radar part of the spectrum. This is the one thing which is used in the ground penetrating radar method, and another is a broad range of low frequency, a broad range of low frequency extending from audio frequencies to the signal with period of hours, days, and years. And this is used in the electromagnetic induction method. Okay, so two ranges are very, very important. The first range in the high frequency in the sense megahertz up to gigahertz range, and this is used in the ground penetrating radar method, GPR method. Okay, and the second thing is low frequency range, which is used in the electromagnetic induction part, and this extend up to 10 to the power 4 hertz up to some audio and signals up to the periods of hours, days, and years. The electromagnetic equation in these two cases reduces to simple particular ranges, and we will talk about that in a moment. So this equation 4.108, as we have seen in the previous chapter, this is given the equation 4.108. This equation, the decoupled equation for the electric field, del square E equals to mu r mu 0 sigma del E by del T, mu r mu 0 epsilon r epsilon 0 del square E by del T square. Okay, this term must be clear to you. So this equation in the left hand side describe the variation of the electric component of the electromagnetic wave in the space. Space means x, y, and z direction. So as you have seen in the left side of the equation, this is given del square E, and this del square is dependent on the spatial coordinate. And the right side of the equation, so there are two terms. One term is del E by del T, and another term is del square E by del T square. So the right side describe the variation with the time. And so it's a frequency dependent, as you know that the time and frequency are just inversely proportional to each other, right? The first term is the related to the familiar conduction of the electricity in the conductor. Okay, so here we will write the equation so that you can correlate these things. So I'm writing there the equation del square E is equals to mu 0 mu r sigma del E by del T plus mu 0 mu r epsilon 0 epsilon r del square E by del T square. So the first term, this term is known as the conduction term. This term is known as the conduction term. Okay, conduction term of the electricity in a conductor. Maxwell introduced the second term, and it's called the displacement current term. This term is known as the displacement current term. It originated when the charges are displaced but not separated from their atom. Okay, so let's say if there is an atom and there are electrons and they are positive charges, so electrons are not separated from the nucleus, but they are just displaced at a small distance. Okay, causing an electrical polarization. Very very important, polarization. Fluctuations in the polarization have the effect on the alternating displacement current. Now suppose that the electric dipole emitting E and B oscillate sinusoidally with the angular frequency. So we can say that del E by del T we can replace with the omega E, and then del square E by del T square we can replace with the omega square E. This happens when electric and magnetic field component are oscillates with the sinusoidal. Okay, so in these terms we can write del E by del T as omega E, and this thing we can write as omega square E. In this case, we define a parameter known as magnitude ratio, which is defined as MR. So magnitude ratio is defined as the second term upon the first term. The second term, which is the displacement term, to the first term, conduction term, in दोनों का जो ratio है, that will be defined as the magnitude ratio. And if we cancel out these terms, epsilon 0 to epsilon 0, mu 0 to mu 0, and finally we will get this equation 2 pi f epsilon 0 epsilon r upon में sigma. So what you are finding out from there on, that the magnitude ratio is inversely proportional to the conductivity, and magnitude ratio is proportional to the frequency. So these two terms are very, very important that you must remember from there on. Okay, where f is the frequency of the signal. So there is given first case, the conductivity sigma of the rocks and soils is generally in the range of 10 to the power minus 5 to 10 to the power minus 1 ohm inverse meter inverse. This question can be asked in the interview, that what is the order, typical order of the conductivity of rocks and soils? Then you will say 10 to the power minus 5 to 10 to the power minus 1 ohm inverse meter inverse. And if you have to ask in the interview, that what about the ore bodies? So ore bodies are the conducting body, and for the conducting body, conductivity will be higher. Okay, so sigma may be larger, and this larger quantity will be 10 to the power 3 to 10 to the power 5 ohm inverse meter inverse. So let's say for the next is given there, the electromagnetic induction surveying is usually carried out at frequencies below 10 to the power 4 hertz. So the electromagnetic induction का जो survey हम करेंगे, that will be carried out at frequencies less than 10 to the power 4 hertz, for which the magnitude ratio is much less than unity for both the good and bad conductors. So magnitude ratio, if you will put the frequency will be there 10 to the power 4, and the conductivity की अगर आप value put करो 10 to the power 3 to 10 to the power 5, then these quantities are going to be cancelled out, and this magnitude ratio will be much less than unity. Okay, at these frequencies, this is very, very important term. At these frequencies below 10 to the power 4 hertz, electromagnetic signal passes through the ground in a diffusive manner. This is very, very important. Why this is given the diffusive manner? Because magnitude ratio for this condition, which condition? The condition in which the frequency is less than 10 to the power 4 hertz. Let's say this is 10 to the power 4 hertz, less than 10 to the power 4 hertz, so you can say 10 to the power 3 hertz, and you have a conductive body, then sigma will be 10 to the power 3 to 10 to the power 5. So this magnitude ratio will be less than unity, and what the magnitude ratio suggests is the ratio of the second term to the first term. If this is less than 1, that means the second term can be neglected. That means the del square E, the equation will contain only the first term, mu 0 mu r sigma del E by del T. And this equation is the familiar diffusion equation. Okay, this thing is must be clear to you. This equation is the familiar diffusive equation by conversion of the changing magnetic field to the electric current and vice versa. This is the first case. This was the first case. Now talk about the second case, in which frequency is high enough. In the first case, we have taken the frequency less than 10 to the power 4 hertz. In that case, the method was electromagnetic induction. Now we are talking about the second condition, in which the frequency is very, very high. High frequency surveying employ the radar signal. Basically, they are going to use the radar signal with the frequencies, very, very important, around the 10 to the power 8 hertz, or you can say gigahertz to megahertz. Or in this case, magnitude ratio mr will be in these conditions, the electromagnetic signal propagate like the wave. In that case, magnitude ratio is very small in the ore bodies. Or in case of ore bodies, magnitude ratio is small, but for the another one, this can be greater than unity. And if the magnitude ratio is greater than unity, in that case, that means the second term is dominant term, right? You can say the second term is dominant term. In that case, the first term will be negligible and the second term will be effective there. So you can say mu 0 epsilon r mu r del square E by del T square. And this is the familiar wave equation. So this, in that case, the electromagnetic signal will propagate like a wave and is subjected to the diffraction, since you know that it is a property of the wave to diffract, to refract, and the reflection. Right. I think this is clear to everyone. Now we are going to talk about the first electromagnetic method, which is known as the electromagnetic induction. Okay, very, very important. Mains exam mein there will be the question of at least 50 marks. Describe the electromagnetic induction method. So you have to talk about these things. So let's see what is given there. So let's see. The first question that can be asked in the prelims is given there. The electromagnetic surveying carried out at frequencies below 50 kilohertz are based on the principle of electromagnetic induction. तो प्रीलिम्स का फर्स्ट क्वेश्चन आपका बनेगा कि जो इलेक्ट्रोमैग्नेटिक इंडक्शन है वो किस फ्रीक्वेंसी रेंज में वर्क करता है. Then you will say that it will work in the less than the 50 kilohertz. What happens in the method is given there, the process is given there. An alternating magnetic field in a coil, or you can take a cable also, induces an electric current in the conductor. Let's say you have a conductor and you are supplying some alternating magnetic field through the coil, through the cable, then it will induce an electric current in a conductor. The conductivity of the rock and soil is too poor to permit significant induction current. If there is a rock, then the current will not pass through this. But this is very, very important. When a good conductor is present, this is the very, very important. And that's why the electromagnetic induction method is used there. If the good conductor is present, the system of eddy current is set up. Okay, you know that what the eddy current means. So if there is a conductor and you are supplying some alternating magnetic field, then alternating magnetic field will induce an electric current, and this electric current can be passed through the conductor. And when this pass through the conductor, it will set up some eddy currents. These eddy currents produce a secondary magnetic field that are superposed on the primary field and can be measured at the ground surface. Okay, so the diagram is given there. You can easily understand this by using this diagram. So let's try to understand what is given there. So this is the surface. This is the Earth surface. You have a transmitter there. Transmitter can be a coil or it can be a cable in which you are producing changing magnetic field which will produce the electric current. So there is a transmitter, so there are the electromagnetic waves are propagating, and there is a receiver which will receive the electromagnetic signals. Okay, so what will happen? This is the surface, and beneath the surface, below the surface, let's say there is a conducting ore body. So if there is a conducting ore body, electromagnetic wave will pass through the transmitter, it goes below the surface and it will pass through the conductor. And during this process, this will induce an eddy current. And this eddy current in general will produce a changing magnetic field, and which will be passing through the secondary coil, and this is the receiver, and this is going through the receiver. Okay, so basically there are two signals. One is the primary signal which is transmitted to the transmitter. Another is the secondary signal which comes from the eddy current, and there is a phase difference phi between the primary and the secondary electromagnetic wave, and there is a difference of the amplitude also. These things are very, very important. Okay, so we'll understand this, how they are important. So in case of the electromagnetic induction method, as we have seen, the magnitude ratio will be less than 1, will be less than 1. In that case, second term will be negligible, so only first term will remain. So for the magnetic field condition, you can say the del square B. We have taken only the Z component, so this can be converted into del square B by del Z square. Second term we have neglected, so only remaining the first term is there. Where the magnetic field has the component Bx and By, the form of the equation is reminiscent of the one-dimensional equation of the diffusion, or you can say the heat conduction equation, right? So the solution of this equation will describe how the temperature, or you can say how the magnetic field will be changed. Right, so this is given there. The component Bx component and the By component are given there. So Bx and By component, how these are changing with respect to the time. This is given there. And there D is defined as the skin depth, and the formula of the skin depth is given there. The two things you must remember, that the skin depth depend on the two factor. The first factor is the electrical conductivity, and the second factor is the frequency, angular frequency. So this is very, very important concept, that the skin depth is D. And what is the mean of the skin depth? It means that this is the depth at which the magnetic field is attenuated of 1 by E. That means E inverse. That means 37% of its original value. And its original value means the value outside the conductor. Okay. So the skin depth is dependent on the two factors. One is the conductivity of the body, and another factor is the frequency of the field. The skin depth in normal ground, if you have the normal ground, in that case this skin depth will be very low, or you can say it's about 50 meter or so. And for the ore body and for the conducting body, the skin depth will be approximate 16 centimeter. Okay, so this thing must be clear to you. This formula is very, very important. There will be a 101% question on the prelims exam depending on this formula. There was the question in 2021, there was the question in 2020, there was the question in 2022. So this year the question will also be asked from this formula. The important thing is there that the skin depth is not the maximum depth of penetration. So there are two concepts that must be remembered to you as per the men's exam is considered or the interview is considered. The one thing is the skin depth. The one thing is the skin depth, and the another concept is the depth of penetration. Both these two are the different concept, depth of penetration. So the skin depth is defined as the depth at which the magnetic field is reduced to 1 by E of its original value, and depth of penetration is defined as how much the magnetic field can penetrate through the conductor. Okay, so basically let's see, skin depth is not the maximum depth of penetration of the magnetic field, but it helps to indicate how rapidly the field is attenuated. But magnetic field is effective at depths that are many times of the skin depth. So this is also important that magnetic field will decay up to 1% at the depth of 5 skin depth, and it will decay up to 0.1% up to the depth of 7 skin depth. So this is the practical depth of exploration of the induction method. So this is the limiting the practical depth. Then they're given the manifold method of the electromagnetic induction have a common principle. And what is the common principle? This is given there. Very, very important concept. A coil or a cable is used as a transmitter. We have used a coil or the cable as a transmitter, as you can see from this diagram, and you can relate this theory from there on. Is used as a transmitter of the primary alternating current. This is the primary alternating current, and this is generated by this transmitter T, alternating magnetic field, while another coil that is known as the receiver serve as a receiver of both the primary signal and the secondary signal from the ED current induces in a conductor. Okay, so this receiver will receive the primary signal through the transmitter only, and the secondary signal which are produced by the ED current in the conductor. Now the important thing is that the magnetic field in the conductor experience a phase shift. This is very, very important. So the conductor के अंदर जो magnetic field pass होगा, that will experience a phase shift, which is given there. You can see in the diagram. And this phase shift is equals to Z by D. As you can see this equation also, when we have solved the solution, then there is a term Z by D. So this term will denote the phase difference, phase of the magnetic field in the conductor. This is due to the conductivity, right? This result in a phase difference phi between the secondary and the primary signal in the receiver. The exact theory of the electromagnetic induction is complicated, but in the simpler situation is given there. So in the men's exam, if the derivation comes of the electromagnetic induction, then you have to write from there on. Okay, so let's see what is given there. Let's say this diagram is very, very important, and this theory you can relate from this diagram as well. Let the current system in the transmitter, receiver, and the conductor. So the current in the transmitter, receiver, and conductor are represented by IT for the transmitter current, IR for the receiver current, and IC for the conductor current. Okay, now what happens? Let's see. If the currents are sinusoidal, okay, that's very, very important concept. If the current are sinusoidal, then we can express the current in this form, right? Then we can relate that the first derivative of current will be I omega times iota omega times current. Now let's see what is given there. Now you have a conductor. So there are two properties, two resistive things that are going to become in the conductor. One is due to the resistance and one is due to the inductance. Okay, so let's see what is given there. The resistance of the conductor be R and the self-inductance be L. The voltage VC in the conductor, the voltage VC in the conductor is composed of two parts. That's very, very important. One is the resistive part and another one is the inductive part. So resistive part due to the current IC in the resistor R is equal to ICR, and the inductive part due to the change of current, that is equal to LD IC by dt. So the complete voltage in the conductor will be VC, that will be equals to ICR due to the resistive part, and LdI by dt due to the inductive part. Okay, and di by dt you can write iota omega IC, because I is in the form of exponential iota omega t. Okay, so you will get this equation. Now we will use the concept of mutual induction. The voltage VC is induced in the conductor by the changing current. Right, in the conductor, as you can see in the diagram, the current voltage in the conductor is induced due to the transmitter. Right, so there will be a mutual effect, and the induced current, the AD current, is going into the receiver. So there is also a mutual inductance, and there is a mutual induction between the transmitter and the receiver. So there are three mutual induction. The first between the transmitter and the conductor, the second between the conductor and the receiver, and the third one between the transmitter and the receiver. So we are going to use these three mutual inductions. So these are given there, that the mutual induction between the transmitter and the conductor will be MTC. Okay. Similarly, the transmitter current induce a primary voltage VP minus, there is a mutual induction between the transmitter and the receiver also, and there is a mutual inductance between the receiver and the conductor also. Okay, so we will use these equations and this equation, then we'll, the final result what we get is, this is written there in the next page. So the final result is given by this formula. This is very, very important formula, where the beta is defined as omega L by R, which is known as the response parameter. This is known as the response parameter. This term is also very important. We will talk about that in a moment. The beta equals to omega L by R is the response parameter of the conductor. The function in the parenthesis is a complex number, very, very important. Why? Because there is a term of iota, right? So this term we can write as a plus iota b, or we can write as p plus iota q. So we can write it as in p plus iota q, where the p is the real part, which has the same phase as the primary signal, and this is known as the in phase component, real part, and the imaginary part, which is given by the q term, which that means the out of phase, that means the 90-degree phase is there with the primary signal. Okay, and this term is known as the quadrature component. So there are two components. One is the in phase component, another one is the quadrature component. In phase component, that means the phase difference is zero, that means the same phase as the primary signal. Quadrature component, that means out of phase, that means 90-degree phase between primary and the receiver signal. Now, how will you do the electromagnetic indexing survey is given there. So first thing that you have to remember, that this is the diffusive equation, right? And the diffusive, another diffusive equations are given there, the gravity, magnetic, geothermal, seismic, these all are the diffusive techniques. Okay, and electromagnetic induction, this is very, very important. This can be asked in the interview, a question, that electromagnetic induction is an average value of the electrical conductivity. It will not give the conductivity of a particular rock, but it will give the average conductivity of a volume, right, for a particular volume. But the resolution is better than the potential field method. This is also very important concept, that the potential field methods, which are the gravity method and the magnetic method. So electromagnetic induction method has the greater resolution than the potential methods. The next important thing is that the electromagnetic induction is very suitable for the airborne survey. How you will do the airborne survey is given there. These are carried out originally with the fixed wing aircraft. The first thing that you can use the fixed wing aircraft, and the second thing you can use the helicopters. Okay, so both are good. You can, and the transmitter and the receiver coils are mounted usually with their axis coaxial or parallel to the line of flight in a fixed position in an aircraft, or it is towed as a bird using the configuration. And this is given in the magnetic field chapter, and we can draw it here also. Here we will draw that. Let's say this is the helicopter. Okay, let's say this is the helicopter. So what will happen? The transmitter is there and the receiver is there. Okay, so there will be the difference, there will be a distance between the transmitter and the receiver, and this helicopter is moving in this direction. So this figure is defined as the bird view, the towed bird view using the configuration, right? The next thing which is important is, this term is very, very important. The increased separation of the transmitter and the receiver in this configuration give the greater depth of penetration. Very, very important concept. If you have to penetrate deeper inside the earth, then the transmitter and the receiver distance must be larger. Okay, this is very, very important concept. Then see what the next is given there. So as a transmitter, you may use a long cable or a large horizontal loop on the ground. That doesn't matter much. In the form of a receiver is usually a small coil. It can be used to detect the direction. The first thing you can detect the direction. The second thing you can detect the intensity. The third thing you can detect the phase of the secondary signal. So these are the three things you can detect: intensity, direction, the phase of the secondary signal. So this is the slingram method or horizontal loop method given there. This is the earth surface, and there is a transmitter and there is the receiver, and they are at a distance L, and they are attached by a long wire, and there is a conductor beneath the surface, below the height h, and having the width s. Very, very important. Okay, so this is the configuration of the horizontal loop method or slingram method or ronca method, and this is the particular diagram. The graph between Vs by Vp, the secondary voltage and the primary voltage का जो ratio यहाँ पर है वो x by L. X is the distance of the conductor from the center of this transmitter receiver system. Okay, so this graph is there, and this graph is explained here. So this is written there. The explanation is given there. The method are illustrated by the horizontal loop electromagnetic method, HLEM, or this is also known as the slingram method or the Ronca method. Okay, and the theory is given there. You can just read about that. Very simple theory is given there. Okay, doesn't much bother you. So this was all about the electromagnetic induction. So the most important thing about that is written there. The most common use of the electromagnetic induction method is in the lateral profiling. Very, very important concept. Electromagnetic induction method is used in the lateral profiling. In the environmental application, it is useful to locating the buried pipes that may carry fluid, gas, ground-based electromagnetic method. Also used for the vertical sounding, and this concept is very, very important, as we have seen previously. The greater the separation of the transmitter and the receiver, the deeper is the maximum depth at which conductor may be analyzed. So this is very, very important concept that you must remember. An important form of the vertical electromagnetic sounding is the magnetotelluric method. So we will talk about the next topic is the electromagnetic magnetotelluric sounding, right? So this is the electromagnetic sounding method, vertical sounding method. And the most important thing that will be asked in the prelims exam is that what is the advantage of the magnetotelluric sounding method? Magnetotelluric method is that it has the penetrative ability at low frequency signal from natural sources in the external geomagnetic field. So magnetotelluric method के बारे में आपको तीन चीजें ध्यान रखनी है. The first thing that it will use at the low frequency. The second thing, it has more penetrating power. The third thing is that it uses the natural source of current. Natural source of current, and we will talk about that. What is this natural source means basically. So let's see from here on. The magnetotelluric sounding method is given there. The magnetotelluric sounding is a natural source electromagnetic method. So first thing is the natural source method. The fluctuating electromagnetic field that originate in the ionosphere. This is given the origin of that particular thing. Very, very important concept is there. And there will be the question in the prelims from this topic. The fluctuating electromagnetic field that originate in the ionosphere. So you know that in the ionosphere, the fluctuating electromagnetic field originate, and this originated electromagnetic field are partially reflected at the Earth's surface. Let's say this is the surface of the Earth. Let's say this is the surface, and this is the ionosphere. This is the ionosphere. So there is a fluctuating electromagnetic field is creating. By that, an electromagnetic wave is incident on the surface. This wave will be reflected. This reflected will again goes there and again reflected. And through this process, we can say there is a vertical component of electromagnetic field. Vertical component. So this is given there. The fluctuating electromagnetic field that originate in the ionosphere are partially reflected at the Earth's surface. The returning field are again reflected off the conducting ionosphere. This happens repeatedly so that the field eventually have a strong vertical component and may be regarded as a vertically propagating plane wave with a wide spectrum of frequencies. These fields penetrate into the ground and induce telluric current. Very, very important concept, which in turn generate the secondary magnetic field. The telluric current are detected with two pairs of electrodes, usually oriented in north-south direction and the east-west direction. This is very, very important thing. Three components of the magnetic field are measured. तो this concept आपको ध्यान में रखना है. मैग्नेटोटेलरिक मेथड में आप तीन तो मैग्नेटिक फील्ड के कंपोनेंट मेजर करते हो और दो इलेक्ट्रिक फील्ड के कंपोनेंट मेजर करते हो. मैग्नेटिक फील्ड के कंपोनेंट बी एक्स बी वाई बी जेड मेजर करते हैं. इलेक्ट्रिक फील्ड के कंपोनेंट ई एक्स एंड ई वाई मेजर करते हैं. ओके, so this is given there. The three component of the magnetic field are measured: the vertical component bz and the horizontal component parallel to each of the telluric component, that means bx and by. The method yield the conductivity information from much greater depth. This is very, very important concept, that through the magnetotelluric sounding we can approach greater depth. It is used for the search of petroleum and deep zones for the mineralization in the upper crust. The next thing is given there. The long period magnetotelluric method में long period होता है 10 to 10,000 seconds होता है. It is an important method for investigation of the structure of the crust and the upper mantle. Okay, so this is also important thing. From there on, the theory is given. So there will be the question in the mains exam of the 10 marks. Then you have to start from there on the theory. The basics you will tell about the magnetotelluric method, and then you will start the theory part. So let's start the magnetotelluric method from there on. Consider a plane electromagnetic wave propagating in the z direction. Why we have considered that? Because in the magnetotelluric method, we are using the magnetotelluric current. This is the surface, this is the ionosphere. Through the ionosphere, fluctuating magnetic field will produce the electromagnetic current, goes to the surface, reflected back, reflected from the ionosphere, reflected again. So there will be a large vertical component. This is in the z direction. Let the electric field component Ex be along the x-axis, so that the magnetic field By is along the y-axis. Ampere's law relate the x component of the electric field to the gradient of the y component of the magnetic field in the z direction. So this is the equation from the Maxwell's law. According to Ampere's law, the del cross B part, you can see the del cross B part is equals to mu j, mu 0 j plus mu 0 epsilon 0 del E by del T. Right? From there on, we can find out that equation also. By is the given the form in equation 4.111. So differentiating by parts, so by is given there, and when we will solve this equation, finally we will get this equation. This is very, very important for the Ex part. So there is a term of pi by 4, that means 45 degree. So for the magnetic field in the x direction, magnetic field, so comparison of equation 4.11 and 4.12. You can see the equation 4.111 here. Let's check it. So there is the equation 4.11. So remember this, इसको mind में रखो, इस equation के form को, cos omega t minus z by d. Then there is exponential term, then there is a b node, and this is equation for the bx and by. Now comes to the equation for Ex and Ey, and now we will relate these two equations. Okay, so we remember that equation in mind so that you can easily relate this equation for the Ex component. So the same B0 part is there, the same exponential part is there, the same cos part is there, omega t minus ZD. The extra term of pi by 4 is there. And this extra term of pi by 4 shows a phase shift between the Ex and By component. Okay, and the maximum amplitude of the two component, the Ex part and the By part, from that equation, if we will find out the ratio, then we will get this equation. And if we will put the d value and the sigma value, then we will get these two equations for the effective resistivity rho at depth d. Okay, so the analysis gives the similar result for the electric field along the y-axis and a corresponding magnetic field along the x-axis. This equation we have found for the electric field in the x direction, magnetic field in the y direction. Similarly, we can find the equation for the ey and bx. Okay, addition to the horizontal magnetic field Bx and By, the vertical component of Bz is also recorded for use of the interpretation of two-dimensional structures. तो हमें देखो यहाँ से क्या मिलेगा, दिस इज वेरी वेरी इंपॉर्टेंट सर. ये एक क्वेश्चन बनता है, प्रीलिम्स का क्वेश्चन बनता है, ध्यान रखिएगा, इंटरव्यू में भी पूछा जाता है. The data set from the magnetotelluric site will consist of 5 terms. The 5 terms are which 5 terms? Two terms for the electric component Ex and Ey, and then 3 terms for the magnetic field, three magnetic field component Bx, By and Bz, recorded continuously during a lengthy observation interval covering some hours of the day. The recorded magnetic field consists of an external part from the ionosphere and an internal part related to the induced current distribution. These components must be separated analytically. So these are the things given there. I think the magnetotelluric part is clear to you. This is the physical diagram of the magnetotelluric method. How you will determine the structure is there. The seismic reflector are given there. The water is there, and all these stuffs are given there. You can check it. So the next thing which is important is the interpretation of magnetotelluric data is done by the two methods. The first method is the modeling, and the second method is the inversion. In the modeling method, it's a direct approach solving the conductivity distribution. So you can check it from there on. Modeling and inversion. And the next thing is given, magnetotelluric sounding can be carried out in the sub audio to audio range. So this range must be clear to you. Sub audio up to audio range, 10 to 10 to the power 4 hertz. Its main application is in detecting the electrical conductivity at greater depth. Very very important, greater depth, using a very very low frequency, very frequency less than 1 hertz. So 1 hertz up to 10 to the power 4 hertz. The investigation of resistivity in the crust and the upper mantle using the magnetotelluric sounding is illustrated, and this thing is given there. So as now we have talked about the first, the electromagnetic induction method. The second thing we talk about magnetotelluric method. In the magnetotelluric method, we determine the Ex, Ey, Bx, By, Bz component, and the frequency is from 10 up to 10 to the power 4 hertz, and for the much greater depth we can take the frequency much less than 1 hertz, right? In the electromagnetic induction method, we are taking a transmitter, a receiver, and if there is a conductor beneath the surface, then the conductor will induce some eddy current, and this eddy current will induce an electromagnetic wave, and this can have a phase difference with the primary wave, and this phase difference we can find out. So these are the things. The third and the last topic in the electromagnetic method, the ground penetrating radar method. This is also very important method, ground penetrating radar method. So the one thing that you will remember, that the ground penetrating method is used at the high frequency. Okay, so in that case, if we will use the high frequency, we know the equation for electric field del square E, which have two terms, right? The first term for the del E by del T, and the second term for the del square E by del T square. So in the ground penetrating radar case, we will take the high frequencies. in that case we have defined a magnitude ratio. Okay, so magnitude ratio is defined as the second term upon the first term, and in the high frequency range, since the magnitude ratio will proportional to the frequency, so for the high frequency magnitude ratio will be large, that means second quantity will be large, that means we can neglect the first quantity, that means we can neglect this quantity, so we will take only the second term there. So this will be the equation. This is the spatial variation, this is the time variation, and this equation is the similar wave equation. Very very important thing, this is the wave equation. And the wave equation, यहाँ से आप velocity determine कर सकते हो basically. So comparing this equation with the seismic wave, we will get the velocity of the wave. In the vacuum, if you talk about, the speed of light is 1 upon under root mu 0 epsilon 0. And we know that epsilon is k times mu 0, where k is the dielectric constant. So you can take this formula also. Dielectric constant, it's normally for the earth material is 5 to 20, but for the water, this is 80. So for the rocks, minerals, the electromagnetic wave velocity is from 0.2 c to 0.6 c. Okay, to simplify the discussion, the del square E part will contain three terms. Del square part contain del square by del x square, del square by del y square, and then del square by del z square. For the simplicity, we are taking only the z component. Okay, so that means this equation will convert into one-dimensional equation. So we can write this type of equation thereon. And if you will compare this equation with the wave equation, and if we'll solve this equation, we will get the electric field component like that. F is the frequency, Z is the wavelength. Okay, lambda is the wavelength, F is the frequency, and frequency time wavelength is known as the velocity of the wave. So moving into the next thing. So as we have seen there, the high frequency electromagnetic wave travel in the ground as the seismic wave. It travel as a wave. So instead of being determined by the elasticity parameter in the seismic wave, the velocity is given by under root Young modulus upon my density, right? So this depend on the two parameter, the elastic parameter and the density. But in case of electromagnetic wave, the propagating is not going to depend on the elastic parameter, but this is dependent on the dielectric property of the ground. This is very very important concept. So prelims में एक बार क्वेश्चन आया हुआ है कि जो ग्राउंड पेनेट्रेटिंग रेडार मेथड है, जो जीपीआर मेथड है, उसमें व्हाट द फिजिकल क्वांटिटी वी आर गोइंग टू मेजर is the dielectric constant. Dielectric constant. Why? Because the velocity is dependent on the dielectric constant. As you can see from the previous page, there is an equation. You can relate it from there on. For the velocity, there is an equation. Let's see. This equation you can see. This equation for the velocity, right? This is very, very important. So the velocity is dependent on the dielectric constant. You can see from there on. So this is the ground penetrating radar method, GPR, जिसको हम जियो radar भी बोल सकते हैं. And this GPR method is used the familiar echo principle, used as in the seismic reflection seismology, and we use a very very short radar pulses lasting 10 to the power minus 8 seconds, emitted by a mobile antenna on the ground surface. Okay, so the process is given there, and next thing is so the main चीज is from there on. यहाँ से देखिएगा important जो चीज है, depending on the composition of the soil and rock. What is the composition of the soil and rock? The nature of the subsurface texture and the frequency of the radar signal. Depending on the first thing, the composition of the soil and rock. The second thing is the nature of the subsurface texture. And the third thing is the frequency of the radar signal. The effective penetration depth may be up to 10 meters. This is very, very important concept. The effective depth of penetration for the ground penetrating radar is up to 10 meters. Although we can extend this up to few meters also. This is restricted up to the few meters. And the frequency range we are going to use is up to 10 to the power 8 to 10 to the power 9 hertz. And this is used for the high resolution. Very, very important. ये क्वेश्चन आपके एग्जाम में पूछा जाएगा कि जो आपका ग्राउंड पेनिट्रेटिंग रडार मेथड है लो डेप्थ तक मेजर करता है, इसकी डेप्थ ज्यादा नहीं है, पेनिट्रेशन की जो डेप्थ है वो कम है, बट इसका रेजोल्यूशन हाई है. द वेरी वेरी इंपॉर्टेंट थिंग इज दैट इट हैव द हाई रेजोल्यूशन. So this is written there. Despite its limited depth of penetration, although its depth of penetration is limited, but it gives a high resolution. This make it a powerful tool for the near surface geophysical exploration. Very very important. Exam में question पूछे आपसे कि near surface geophysical exploration में आप which method you will use, then you will say that you will use the ground penetrating radar method. So friends, this is all about the electromagnetic method. We have talked about three methods. The one we have talked about the electromagnetic induction method, and the second we have talked about the magnetotelluric method, and the third we have talked about the ground penetrating radar method. I think this is clear to everyone. In the prelims, there will be approximate 2 to 3 questions, and in the mains exam, there will be definitely 2 questions up to 10 marks. So 20 marks question will be there from in the mains exam, and 1 to 2 question will also in the interview part. So this video is going to be very very helpful for you. So thank you very much. If you have any doubt, you can put in the comment box and we will try to solve them.